Great. Okay. I hope you can all hear me okay. Apologies again for the scratchy voice, but if I'm too quiet, let me know and I can maybe use the handheld mic as well. Um, so it's great to see so many of you here and taking interest in this kind of topic of women in astronomy. So my name is Yvette Perrott. I'm from Victoria University of Wellington and I'm an astronomer by profession. So I do radio astronomy. I use big radio telescopes from around the world to look at various sort of distant objects. Galaxy clusters are what I'm mostly interested in, which are the biggest objects in the universe. So, but I'm not going to talk about my research today. And when Anne invited me to give this talk, she said that it was Women in Astronomy Month. And so I thought, excellent, I'll give a talk that I have been wanting to put together for a while on women in astronomy. However, doing a Google search, Googling Women in Astronomy Month, I wanted to see if there was anything else going on for this month. Google AI handily informed me that yes, it is Women in Astronomy Month and Wellington Astronomical Society are hosting a talk. I thought, oh, that's a bit strange that that's the first thing to come up. So I'm not sure it actually is Women in Astronomy Month, but this tells me two things. One, that Anne French has the power to unilaterally declare that it's Women in Astronomy Month. And two, that you shouldn't trust Google AI, which we probably all know already. But anyway, very glad to give this talk. So hopefully we're going to switch to the next slide with any luck. All right, so this talk was sort of semi-inspired by this quote, and it's paraphrased a little bit, but anyone who was at the Rassens conference a couple of years ago will probably remember this moment and knows when someone who shall remain unnamed made a statement along these lines, that women didn't make astronomical discoveries back in those days. It's just how it was. So that kind of hurt the soul of a few of us there. We took a little bit of exception to this. And so I wanted to take this opportunity just to bust some of those myths. So we're going to do a little exploding of that concept today. And hence the subtitle of my talk, no, it's not just how it was. All right, so I want to just have a little disclaimer that this is going to be a kind of personal and incomplete tour of the subject. It turns out that you can't fit everything about women in astronomy in a 45-minute talk. Imagine that. So these are some of my kind of personal favorites that I've picked out. They are in vaguely historical order, going from past to present, but I will jump around a little bit. And I will also apologize that it's a bit Eurocentric as well. And that is probably just because I didn't have enough time to do research on this. With a bit of digging, I'm sure there are many women astronomers in the eastern areas of the world as well. So no claim to completeness, but hopefully some interesting stuff. All right, so I think when I first thought of this topic, the earliest astronomer that I thought of was Sophia Brahe, and that was in the blurb that Anne sent out. But actually I realized that there were earlier women astronomers, of course. And so the earliest one that I came across when I was doing a little bit of research was Hypatia of Alexandria, who I'm sure many of you will have heard of. Very famous, well-known woman scholar associated with the Alexandrian Library, I guess. And I think probably she is the first female astronomer. There may be some earlier astronomers in kind of Egyptian, Mesopotamian times, I don't know, but she was the first one I could really find anything about. So she became head of this Platonist school of thought in Alexandria around 400 AD. And she is described as a philosopher, astronomer, and mathematician. She is obviously also a magician and makes the lights flicker. So that's fun. So it was kind of hard to find the actual things that she did, the actual things that she contributed, probably partially because it's quite a long time ago and we don't have that great records remaining. But it seems the consensus was that she was more of a teacher and a commentator than an innovator. So it wasn't that she was necessarily making new discoveries, but she was definitely refining existing discoveries, commentating on them, teaching them. So for example, she is known to have constructed astrolabes, which are a device for sort of locating where you are with respect to the sky. But she didn't invent them, they were already invented. But being able to construct them is a fairly massive accomplishment on its own. She's also thought to have edited Ptolemy's Almagest, which was a description of the geocentric model of the universe. So the idea that the Earth was at the center, the sun and all the planets went around it, and some sort of rough tables and equations and calculations showing how that could work. And so she was thought to have edited it and refined it a little bit. Sadly, it's probably quite well known she met quite a brutal death due to political or religious tensions at the time. There are kids here, so let's not go into any more details, but it wasn't a happy ending to her life, unfortunately, which is unfortunately a little bit of a theme of this talk for many of the women astronomers that I'm going to mention. Okay, so skipping forward quite a bit in time, then to the first female astronomer that I had originally thought of when I proposed this talk. Sophia Brahe, she lived from 1559 to 1643. She was a Danish noblewoman, incredibly accomplished in many different fields. So she was a very experienced and accomplished horticulturalist as well, as having knowledge of astronomy, chemistry, and medicine. So she worked alongside her brother, Tycho Brahe, and Tycho Brahe you may have heard of. He's a bit more well known. He's very well known for making very precise measurements of the positions of the planets over time. And those were eventually used to calculate their orbits and went towards the eventual heliocentric model of the universe that we have now. So interestingly, Tycho was quite enlightened for the time. She was his sister, and he trained his little sister. He trained her in horticulture and chemistry, but he actually discouraged her from studying astronomy originally. So she decided to learn astronomy on her own, and read books in German and paid out of her own pocket for works to be translated from Latin so that she could learn astronomy. Eventually, he sort of relented, and she assisted him in many, many astronomical observations. So one of the most famous observations that he made was the observation of a so-called new star, which I'll talk a bit more about in the next slide, and a lunar eclipse as well. And she also assisted in making measurements for Tycho's orbit studies. So he had quite a few assistants who assisted him with making these observations and these measurements. And although he's the one who has sort of gained credit and been renowned through the years as being the one who made these measurements, actually he didn't do all, if any of them himself. It was his assistants, including his sister Sophia. So Tycho's supernova. So these are massive stars that explode at the end of their lifetime, briefly become the brightest thing in the sky. And so he discovered this new star and recorded its position. Over time, what they do is they leave behind a sort of expanding shell of gases. And so over time, you can track the expanding shell of gases, which is quite cool. And so this is a modern picture of the supernova remnant, the shell of glowing gas that's left behind. It's so hot and energetic that it's glowing in the X-ray. So this is an X-ray telescope image of the supernova. And you can actually, it has been measured over time, and you can actually measure how fast the shell is expanding, which is pretty cool as well, because there aren't many astronomical objects where you can really measure something changing. So the observations of this supernova were really important because they provided evidence against the geocentric model that I mentioned before. So it was still very much entrenched at the time in kind of science and religious thinking that the Earth was the center of the universe and everything else went around it. But observing, and another part of that idea was that the heavens were perfect and didn't change. So the appearance of this new star showed that something new had appeared, that the heavens weren't perfect and unchanging. And they also had some observations or evidence, can't quite remember, that showed that it was outside the orbit of the moon. So it was further away than, it wasn't something just happening in our own atmosphere, for example. It's definitely something very far away. The orbital observations of the planets, they laid the foundations for the theoretical understandings about orbits and orbital mechanics and gravity, which were later made by Kepler and Newton. So they're always cited as one of the important sets of information that we had that led us to develop our theories of gravity eventually. So interestingly, one of Tycho's objections to Sophia learning astronomy was not actually about astronomy, it was about astrology. So at that time, astronomy and astrology were very much intertwined. Astronomers would take measurements and use them to create horoscopes, and those were taken very, very seriously. They had to be very accurate. They were provided for kind of noble customers. And so Tycho's objection was actually that he didn't think Sophia was up to the complexity of providing accurate horoscopes. But obviously, after some time, seeing how good she was at these observations, he convinced her that actually she could do it. And so she took on a lot more autonomy after these contributions, and she actually took on some of his astrological responsibilities when he was away. So that's kind of funny to think about now, that the astrology was the thing that had to be really accurate and that he was worried about. So King Frederick II sponsored a few observatories for Tycho, and it's known that some were actually for Sophia. So although we all know the name Tycho Brahe, or anyone who studied a little bit of astronomy knows that name, actually a lot of the work was done by his sister Sophia, and obviously he knew that, and he provided observatories for her to continue with her work. A sad thing, I said this sad thing was going to be a theme of this talk. She married an alchemist in 1602. Unsurprisingly, his alchemy was not successful, and so he wasn't very well off. And so she actually lived in extreme poverty. Her family kind of cut her off because they didn't approve of her pursuing science. So her parents cut her off and wouldn't give her money. And so she lived in extreme poverty with holes in her stockings and not enough food. Until the death of the alchemist in 1613, when she was kind of freed with him and went to live with her son, who obviously did something a bit more sensible to make his living, and they could be a bit more comfortable. Okay, so the next astronomer I want to mention is Maria Kunitz, and I have to admit that I actually didn't know about her before I put this talk together. So she's quite interesting to talk about as a successor to Sophia Brahe. She lived a little bit later, from 1610 to 1644, and this is a statue of her in one of the places that she lived in Poland. So she was born in Poland to quite well-educated parents. She married at 13, which obviously I'm guessing was standard at the time, but obviously now is very young. Her first husband died 3 years later, and so she married again in 1630 to her tutor, who was quite a bit older. So by today's standards, it's not a very nice beginning to life. But her tutor was very encouraging, encouraged her to study astronomy. And so she ended up writing this book called Urania Propitia, which was a reworking of some of Kepler's work. So I mentioned that Kepler took the observations by Brahe and made them into a more systematic model of how the planets move around the Earth. So she simplified his work and came up with some less error-prone ways to do the calculations. And so she had recognition throughout Europe for doing this work. Quite a nice little detail that I found was that in the book, her husband wrote a preface to make it clear that the work was hers and he had nothing to do with it, but did mention that he supported her in the work. So I had nothing to do with this, but it's great and I support her, which was obviously a good match, even though he was quite a bit older. Unfortunately, a fire destroyed many of her academic records, so we don't have much remaining of the work that she did, but there are several copies, and by several I mean kind of 10, of the Urania Propitia still existing. All right, so moving on now to moving a bit later in time, and moving on to a name that many of you might be familiar with. Caroline Herschel lived from 1750 to 1848. She was born in Germany. Interestingly, she suffered from typhus at 10 years old, and she grew no taller than 4'3", so she was shorter than me, kind of here. So she was a very short lady, and she lost the vision in her left eye as a result as well. So it's kind of amazing when we go on to talk about the astronomy that she did all this with only one eye, essentially. She received a very cursory education. Her mother thought that she should train as a house servant rather than being educated. After her father's death, she moved to England to live with her brothers, and this was when her education started to be more possible. Her brothers were very involved with music, and so she trained as a singer and had a short career as a singer. And then her brother William, who again, the brother William Herschel is the more well-known of the two, transitioned from music to astronomy, and she did too. And there's quite a sad quote that I found from her memoirs, which is, "I did nothing for my brother but what a well-trained puppy dog would have done." That is to say, I did what he commanded me. So quite sad to think about that. But she did get into the astronomy, even though she felt that she was a little bit forced into it. And so she started out as William's assistant. She did things like grounding mirrors, observing and performing calculations. So obviously very capable and very mathematically capable as well. And she eventually did develop a love for astronomy herself in her own right. So she did many things, which are sort of too many to list, but she discovered comets, she discovered nebulae, some nearby galaxies, and she created catalogues of stars, which is one of the things that she's very well known for. And so she created what became the New General Catalogue. So when you look at objects in the sky, they quite often have a name starting with NGC, and then a number. Those are from the New General Catalogue, which is what Caroline collated. So she has a whole list of firsts against her name. She was the first woman to receive a salary as a scientist, to hold a government position in England, to publish in Philosophical Transactions of the Royal Society, the kind of premier scientific journal of the time, be awarded a gold medal of the Royal Astronomical Society, and be named an honorary member of the RAS. So for someone who started out with this kind of debilitating illness, who was trained as a house servant and never expected to do anything, it's pretty incredible to think about what she achieved in her life. Okay, so this is kind of actually a contemporary. This lady is called Wang Zhenyi. Hope I'm pronouncing that correctly. And I came across her while I was researching this, and I'd never heard of her before. And she's amazing. I think she's my new favorite astronomer, to be honest. So she was pretty much a contemporary of Caroline Herschel, but obviously in a very different part of the world. So she was born in East China to a family of scholars. And the feudal customs of the time actually forbade women from being educated, and her family encouraged her to learn despite those customs. So they really went against the society to encourage her to learn. She's known for her contributions in astronomy, mathematics, but also poetry. And there's what I think is a beautiful example of her poetry up on the right-hand side there. I'll move this out of the way so you can read it. "It's made to believe women are the same as men. Are you not convinced daughters can also be heroic?" I'm convinced. I hope I'll have you guys convinced by the end of this talk. So she was a teacher as well. She was well known as a teacher, and even ended up teaching male students as well, which is pretty incredible when you think that she wasn't really allowed to learn in the first place, and she ended up being so well respected and well known that she was teaching male students. And simplified mathematical works, again, finding ways to do mathematics in less complicated and error-prone ways that had been done previously. Another fact that I love about her is she learned equestrian skills, archery, and martial arts from the wife of a Mongolian general. So not only was she, amazing academically, but she was also pretty physically capable as well. I don't think you'd want to mess with her. So she authored a bunch of different works, including Dispute of the Precession of the Equinoxes, so describing how the equinoxes change their position over time, Dispute of Longitude and Stars, Explanation of a Lunar Eclipse. And she famously did this experiment using a round table in her garden pavilion, which represented the Earth, a hanging crystal lamp, which was the sun, and a round mirror, which was the moon. And so she was able to make them move in kind of astronomically correct ways, and use them to explain how a solar eclipse could occur. And she recorded her findings and observations in this article. She also recognized through observation that Earth was spherical, which was very much ahead of her time. At the time in China, anyway, they thought that the Earth was flat, and published a theory of the Earth's roundness as well. So she was celebrated also for her contributions to poetry, women's education, and gender equality. And again, sadly, died quite young at age 29, probably of malaria while traveling. Okay, so we're going to jump forward quite a bit in time now, and we're going to have a little segue into the world of radio astronomy, because I said this was going to be my personal journey. I'm a radio astronomer, and so I find the beginnings of radio astronomy and the women who contributed to its beginnings fascinating, and so I've sort of concentrated my talk a little bit more on those parts. So I want to talk about Elizabeth Alexander, who you've probably never heard of. She lived from 1908 to 1958. And she was probably the first female radio astronomer, and I've put a question mark there and you'll see why in a few slides. So she was born Frances Elizabeth Somerville Caldwell in Surrey in England, and she spent her early life in India before returning to the UK for high school. She then went to Cambridge University and studied natural sciences, and she took a PhD in geology. So she was really one of the early women to be able to study at Cambridge and have a PhD there. In 1935, she married a New Zealand-born physicist called Norman Alexander, and they moved to Singapore together. From 1940 to 41, she was a captain in the Naval Intelligence Service, and so she worked on radio direction finding while she was in Singapore. And so she moved away from geology a bit into this field of kind of radar and radio, and that's going to be where the connection to astronomy comes in. So in 1942, obviously a fairly significant date, she was evacuated to New Zealand with her children. The idea was actually that she would go and retrieve some radio equipment from Australia, and then take it back to Singapore, but it never happened. She just went to New Zealand with her children. And her husband at that time was missing, and she was informed that he was dead, which was actually not correct, but she didn't find out for quite some time afterwards. So recognizing her expertise, she was made senior physicist and head of the operational research section of the Radio Development Laboratory right here in Wellington. And so while she was there, she worked on a lot of different things in the field of radio and radar research. She was really a pioneer in the field of radio meteorology, so using radio and radar signals to understand the atmosphere and use that to predict weather. And she researched this thing called anomalous propagation, which was where radio rays would be propagated sort of above the curve of the horizon and back down. And so this was a big effect they were interested in during the war for obvious reasons. But the connection to astronomy comes in where she investigated what was called the Norfolk Island effect. So these were observations that were taken from the Norfolk Island radar station. So that's the top station that you can see in the map up there, although I guess it's really off the map. And they found this curious effect in their radar equipment where they would see an increase in radio noise within a half hour of sunrise and sunset. So obviously pretty suggestive that something is coming from the sun. So they did some monitoring from the other stations, which are shown on the map there. And it was a little bit inconclusive, but the quote was that they do seem to indicate that more energy is sometimes radiated from the sun on 200 megahertz. That's a kind of weird unit, but it's megahertz, than would be expected on black body theory. So this is the idea that if you have an object which is a certain temperature, it radiates in a certain way, and you can calculate how much radiation you expect to receive at a given wavelength based on the object's temperature. And so based on knowledge of the sun at this point, you wouldn't really expect to see any radio emission because it was too hot. So it mostly emitted in the optical. Obviously, that's why we see it with our eyes. And by the time you get down to the long wavelengths of the radio, you just don't see anything, right? But these findings were showing that actually they were seeing something from the sun. So there's something else going on than just an object sitting there with a given temperature and radiating in this kind of predictable way. So this was a really important and interesting result. So in 1945, with the end of the war, all of this radar and radio activity in New Zealand pretty much wound down. There were a few remnants, but it did wind down. And Elizabeth returned to England in 1946. So it's interesting that in contrast to most of the other female astronomers that we talk about, she wasn't actually really interested in astronomy, I don't think. Her passion was geology, and she just kind of got sidetracked into this radar business, found something interesting going on with the sun and investigated it for a bit, and then went back to her normal life. And her husband had been found at that point as well, so she was reunited with her husband. But before she left, she wrote up the research in an article called The Sun's Radio Energy, and she noted this interesting thing that there was something extra there that wasn't predicted based on the black body or the thermal emission of the sun. And she had also potentially found a correlation with sunspot number. So if you look at the graph on the left here, you can see my mouse, yep. So this top line here is sunspot number, which goes up and down with time. And the bottom line here is the radio noise. So you can see that there was this great period of very high radio noise, which correlated with this peak in sunspots, possibly this peak here correlating with the next one, but then not much evidence afterwards for a correlation. So it was a bit weak and inconclusive. And this paper was published in a little known NZ-based journal, which had just got started. So it was kind of not made, she didn't make of it what she could have if she was more interested in carrying on with this subject. Later that year and through to 1947, there were reports published by other researchers in Australia, the UK and Australia. So this kind of research was just taking off at this time, really. Some of the research had been done in secret during the war because obviously they were very secretive about the scientific advances they were making during that time. But some of it was actually prompted by her work. So she wrote to some researchers in Australia and said, hey, I've found this interesting thing. And they said, oh, cool, we're going to go and investigate that. And her work has largely been forgotten. So some of them cited the article that she published. The Australian group did, let's give them their credit. But the UK group was sort of famously, I found some interesting comments on the personalities involved, and they sort of famously owned the field and wanted to think that everything they did that was found in that field was down to them. And so they did not cite her work, even though there is evidence that they knew about it. So, like I said, she returned to geology after that, and she went back to the UK, back to Singapore, and then finally Nigeria with her husband, which is a nice ending to her life for once. No sad ending to her life. There is a biography written by her daughter, Mary Harris, which I haven't read myself, but I'm very keen to have a look at. It's kind of hard to get a copy of, but I've just realized that the University Library has a copy, so I will be reading that very soon. Okay, so Elizabeth Alexander, first female radio astronomer, question mark. Ruby Payne Scott, 1912 to 1981, first female radio astronomer, question mark. So Ruby Payne Scott is mostly credited as the first female radio astronomer, although Elizabeth Alexander seems to come a little bit earlier. She was Australian. She was born and educated in Sydney, and actually only the third woman to graduate with a degree in physics that she'd read from Sydney University. So she did an MSc and some research work in medical physics. So that was her first field of interest. And then her research unit closed down and she decided to become a teacher. And that could, not because she wanted to necessarily, but because that was what was open to female physicists during those days. So that could easily have been the end of her research career. But she ended up applying after some time to this company called Australian Wireless Amalgamated, so Australian radio company. And she applied to as a librarian because they didn't hire women as researchers. But she, in what I think was quite a typical manner for her, actually managed to turn it into a research job herself. So she started out as a librarian, then through that librarian job started editing research papers, and then started suggesting ideas, and then started doing the research herself. So she eventually became accepted as a researcher there. At the beginning of World War II, this is when a lot of radio astronomy started because it came out of the radar work that was being done in World War II. She moved into what was known a little bit euphemistically as radio physics. So it was wartime radar research. At the time when she was employed in this radiophysics job, the head of the division wrote a memo on her when she was under some kind of probationary period saying, well, she's a bit loud and we don't think she's quite what we want and she may be a bit unstable, but we'll let her continue and see how she works out. So A, that's terrible. But B, it just speaks to her personality, right? And you can kind of see that in her eyes, I think. She just looks like someone who would be a lot of fun and who would not let anyone get in her way when she decided that was what she wanted to do. So she worked in radar research during the war, but post-war, people were coming out of this radar research with this expertise that they'd gained and wondering, well, what are we going to do now? We want to turn this expertise to some kind of scientific peacetime purpose. And so they had to sit down and think, what are we going to research? What are we going to do? And so she is credited as setting the thinking for the scientific direction of the group. So she was really the ideas person who came up with things that they could do. And in 1946, leading on from Elizabeth Alexander's work, she published some results showing a definite correlation between solar radio emission and sunspot number. So they decided to go in the direction of solar research because of these interesting results coming out of New Zealand, at least in part. And so this is a similar graph to the one we saw in the previous one, but now it's just separated into two parts. So on the top, we have the power, the radio power. So you can see it has this definite peak here, comes down again, some more peaks over here. And compared to the sunspot number for the same time period on the bottom. So peak and sunspots corresponding to peak and radio emission. And it's a bit clearer here than it was in the previous data. But as we all know, correlation is not causation. So we know that there's more radio noise during the times when there are more sunspots, but how do we know if that emission is actually coming from the sunspots or if it's some other kind of related thing that is causing both effects? So to answer this question, she and her colleagues came up with a very clever experiment, which was called the Seacliff interferometer. So this is a picture of the Seacliff interferometer. You can see that there is a radio antenna on top of a cliff. Why do we want to put a radio antenna on top of a cliff? Why is this clever? So what happens is that you get the radiation coming from the sun, which is taking, on one hand is taking a direct path to the antenna. On the other hand, is taking an indirect path where it bounces off the sea and is redirected up to the antenna. And so what happens with this is what you do is you interfere the light coming from the direct and the indirect path, you mix them together. And if the emission is coming from a small region on the sun, you will see some fringes. So you will see some ripple patterns where the light from the two paths is interfering. If it is not coming from a small region on the sun, if it's just coming from the whole sun, you will not see those fringes. Okay, so there's a mathematical reason behind that, and I'm going to go into that a little bit further in a couple of slides. But this is the first interferometer, the first radio interferometer, and we'll talk a bit more about that later. So by using this very clever natural interferometer, Ruby and her colleagues were able to show these fringes. So this is the up and down fringy pattern that you expect when you interfere these two direct and indirect sources of light. It was a bit confusing because it turned out that the sunspots actually were quite often evenly distributed over the sun. So you couldn't actually say that there was one small group of them. But there was a certain time when there was a compact group of sunspots that dominated over all the other ones. And so during that time, they were able to show these fringes. And with a bit of clever mathematics, they were even able to constrain where the sunspots were on the sun. And so this is what these dashed lines here are showing where their observations constrained the sunspots to be within that sort of band across the center of the sun. And you can see that it does overlap with these sunspots which were observed in the optical. So this was quite conclusive evidence that yes, the sunspots were causing the radio emission. And I don't know if I should go, what's the time, by the way? Am I going over? Okay, I will not go into the science, but we can talk about it later if anyone's interested. So she went on to discover 3 out of 5 categories of solar radio burst. And also led the led the development of some new astronomical instrumentation. So kind of an upgrade on this natural interferometer that enabled this a video of the sun to be made. She could image it 25 times per second and make a video and actually track the evolution of these different solar radio bursts. She was also an early advocate for women's rights in the workplace, unsurprising given the little hints into her personality we've already seen. She fought against trivial restrictions like women not being able to smoke by going into an interview smoking a cigarette. They were required to wear skirts, and she said, well, I'm not going up a ladder in a skirt. So she did things like that. A funny but not funny story is that she was married. She got married in secret. She secretly married this man called Bill Hall. But she claimed that she wasn't married, that she was just living in sin, which was very, very frowned upon as well. But the Australian Public Service required married women to resign. So by not marrying, she sort of just dealt with the disapproval of living with this man, but they were actually married. The truth came out eventually, and she was reduced to temporary employee status and lost pension rights. Yeah, so it was pretty terrible because women obviously didn't need a pension if they were married because their husband would have a pension, right? So, and again, a slightly sad ending to the story. She finally had to resign to have children because there was no maternity leave and no flexible working. So if you had children, you were just gone, and maybe you could come back in a few years once the children were bigger, but she didn't. So that was the end of her research career. But again, there is a book. I haven't read this one and I would like to read it. Cool, so now I'm going to jump forward a little bit to a story that probably a few of you are familiar with. Jocelyn Bell Burnell, she was born in 1943. She was born in Northern Ireland. She had an architect as a father who designed the planetarium in her town. So I guess that sort of sparked her early enthusiasm for astronomy. She was only able to study science at primary school because her parents challenged the school policies that said she should learn cross-stitch instead. And she went on to university, attaining also a PhD from Cambridge University. So she worked with Anthony Hewish, who was her supervisor, and others at the Cavendish Laboratory at Cambridge, which I should say is where I did my PhD as well. So you'll see that there are a little bit of mixed feelings with this one. And she constructed what was known as the Interplanetary Scintillation Array, which was a bunch of antennas in a field. And the idea was to study quasars, which are distant active galactic nuclei, which are very active. So they're very supermassive black holes, gobbling stuff up and spitting energy out, which had been discovered quite recently. And her work was very hands-on. So upon entering the faculty, each student was issued a set of tools, a pair of pliers, a pair of long-nose pliers, a wire cutter, and a screwdriver. So it was very much getting out there in the field and building the antennas. So while examining chart recorder sheets from the radio telescope, so her data would come out in these kind of sheets, which they'd have a kind of mechanical pen which would draw. Imagine like an earthquake sensor with a pen which would draw as things wiggled. Same deal for a radio telescope. And so she would get these enormous screeds of paper which she would have to just look through and try and see if there was anything interesting. And see what she noticed was what she called scruff, which repeated very regularly. And you can see it on this sheet of paper here where the arrows are. There are these little spikes here which repeat very regularly. And I don't know if you would have noticed that. I'm a radio astronomer and I would not have noticed that. Let me put it that way. So she was inspecting this data very, very carefully, and she noticed the stuff that was going on. So there was one pulse every 1 1/3 seconds on there. So this was temporarily called Little Green Man 1, not because they really thought it was aliens, but just as a kind of joke. And it was identified eventually as a rotating neutron star. So is my video going to play is the question. Hello. No, maybe the video is not going to play. That's all right. I shall just describe it. So a neutron star is a very dense leftover from a massive star explosion. It's got a very high magnetic field. And so what happens as it rotates is that you end up getting these kind of jets of particles and light being ejected out the poles. And so this thing is spinning. And so as it spins around, you can imagine that these jets of light, they're going to sweep past the Earth. And so as they sweep past, you're going to see it at regular intervals because their spin period is very regular. So it's like a lighthouse spinning, and you see the light pulse as it goes past. So these were an entirely new phenomenon. No one had ever seen these before. No one knew what they were. But she identified it based on these tiny spikes in her radio data. And it became this amazing new field of research. So Bell had to fight to convince Hewish, her supervisor, that the signal was real. In radio data, you often get little bits of interference that are coming from other things that are using similar frequencies around you for communication or whatever. And so Hewish thought that this signal was interference. She had to fight to convince him that it was a real thing. And she said that she was sometimes excluded from meetings held by her supervisor, Hewish, and Martin Ryle, who was the head of the group. In 1974, Hewish and Ryle were awarded the Nobel Prize for their pioneering research in radio astrophysics. Ryle for his observations and inventions, in particular of the aperture synthesis technique, which I'll talk about a little bit more, and Hewish for his decisive role in the discovery of pulsars. So Jocelyn is the research student. She's the one poring over these screeds and screeds of data. She notices that there's something there. She fights to convince her supervisor that it's real. Supervisor gets the Nobel Prize, right? So there was criticism even at the time of her not being included in the Nobel Prize. But she, and I think this is something that I admire intensely about her, she's always been incredibly dignified and never complained about this. She said at the time, I believe it would demean Nobel Prizes if they were awarded to research students, except in very exceptional cases, and I do not believe this is one of them. So this debate goes on today. You will still find people on the internet having very heated debates about this. And you kind of have to make your own mind up about whether you think it was fair or not. But I think there's a general feeling that she was, she had a raw deal. So she, of course, went on to have a stellar career. I won't name all the things, but she's done a lot of things. And there's a whole list of honors and prizes that she's won. In 2018, in particular, she was awarded a breakthrough prize in fundamental physics, which is worth about $5 million. So finally, the recognition for the work that she did. And what did she do with it? She donated it all to fund women, underrepresented ethnic minority and refugee students to become physics researchers. So she's just an amazing, amazing person. Yeah, okay, and it's very unfortunate that her career has been kind of overshadowed by this this thing of being excluded from the Nobel Prize. Did she? Oh, cool. Yeah. Yeah, I wasn't here then. I was. I was at the launch of the International Year of Astronomy in 2009. That's not my photo, but I was there. That was in Paris. So I want to just present as a kind of counterpoint to that story because, like I said, I did my PhD in Cambridge. It's kind of my academic home. I did it in the very lab where she did her PhD. I knew, I met Tony Hewish a couple of times. Martin Ryle had passed on. So it gives me really mixed feelings. I want to present as a bit of a counterpoint of that, another story about women in Cambridge radio astronomy in general. And I've called this Hidden Figures of Cambridge Radio Astronomy because it's a bit like the Hidden Figures of NASA, which the book and the movie has come out recently. And there's a great article by Verity Allen on this, which you can find online. So radio interferometry is a very computationally intensive science, and I'll explain why in a minute. But by 1965, over 45% of the papers being produced in the group had required a computer to process data. And around 50% of the people acknowledged for the computing contribution to those papers were women, right? Women in the Cavendish, like the women of NASA, if you've seen the movie or read the book, they did calculations that were computers, literal computers. So they did calculations by hand, and then they progressed to using computers when they came along. They analyzed photographic plates, not only in astronomy, but also in high energy physics. They prepared scientific diagrams for publication in the days where you couldn't just hit print on your printer and have a nice plot come out. You had to actually draw it by hand a lot of the time. So they did all those things, and they were referred to as the girls in the attic. A little bit condescendingly, but that's okay. A little bit of a segue about radio interferometry. I want to explain a little bit why it's such a computationally intensive science. Probably a lot of you know that the resolution of a telescope, so the fineness of the details that you can observe with it, gets better as the wavelength gets, I've put that around the wrong way, as the wavelength gets shorter. Sorry, that's entirely wrong what's written on that slide. So optical wavelengths, when we look at the light that we see with our eyes, the wavelengths of that light is around of the order of the thickness of a human hair, whereas radio wavelengths are of the order centimeters to meters. So there's a huge difference between the wavelengths that you can, between those two wavebands. So what that means is that if you want to have reasonable resolution with a radio telescope, comparable resolution to your optical telescope, you have to make your telescope ridiculously large. So the biggest radio telescope in the world, the biggest single dish, is called the FAST telescope in China. It's 500 meters in diameter. It's so big you can't even steer it. It's kind of built into a natural amphitheater, and you can kind of move it around a little bit, but it's not fully steerable. And even with that, the resolution is not that great. So what do we do instead? We build a whole lot of littler telescopes, and we link them up, and we synthesize a much bigger one. So this is the Very Large Array in New Mexico, in the US. If you've seen the movie Contact, this is the one. And you can see that there's a bunch of smaller telescopes. They're laid out along these arms. And what you do is you link them up, and you effectively make a telescope with the diameter given by, that would encompass all of them, right? The red circle. That maybe sounds a little too good to be true. And yes, that's an oversimplification. So I want to tell you guys a little bit about Fourier transforms. I really hope this video is going to play, otherwise I'm not going to tell you about Fourier transforms. I'm going to skip straight over it. Nope. Any tech help making your video play? I will talk while we'll see if we can get this video to play. So a Fourier transform is the mathematical idea that you can, any signal, a signal can be like a time series going up and down, or it can be an image like the one I will hopefully show you. You can decompose it into a bunch of waves of different wavelengths. And as long as you have enough waves of different wavelengths, and you can put them together with the right amplitudes, you can decompose your signal into those wavelengths. And hey, we have a play button that looks hopeful. Okay. All right.
Here is an example of a 2D Fourier transform.
I don't want this guy to talk. I want to talk. So let's mute that guy. All right. So what we're going to see here is how this works for a 2D image. So we have this this image of the little girl. Oh, hello. I have a. Okay. Yep. Okay, great. So we have this little girl, and you can see there's this wave going across her face. And this wave has got quite a long wavelength. And what we will see as the movie goes on is that the wave is going to spin around. So to make up the image of this little girl, what you need are a bunch of waves with different wavelengths and with different orientations. So you need to be able to spin them around, and you need to put them together with the right amplitude. And don't worry about what's going on in the middle, but on the right-hand side, what you will see is the image that you make up when you add back those different waves together, right? So at the moment, it doesn't look very much like the little girl, right? This is a long wavelength, so it's picking up kind of the smooth, large-scale structure of the image. And we'll see as we play the video that as we go to shorter and shorter wavelengths, we'll get a better and better reconstruction of the image. Right, so this is just adding up all these different waves with different amplitudes, different like heights of the waves, and eventually, when you get to shorter and shorter and arbitrarily small wavelengths, you get to reconstruct the image pretty well. And even at this point, it's pretty good, right? It's not exactly the same as the original. If you can go to infinitely small wavelengths, then you can exactly reconstruct the image. And this is the theory of Fourier transforms. So I'm not going to play the whole thing. It also does it backwards, which is also kind of interesting. But at this point, you can see with these kind of very tiny, small wavelengths, it's able to reconstruct all the details of her face. And so we're back to the original image almost. So what has this got to do with radio interferometry? It turns out that what a radio interferometer actually observes is the amplitudes of those wavelengths, right? It's not observing the actual sky. It's observing the waves that you would need to reconstruct the sky. And the wavelengths that each pair of telescopes observe, so each pair of telescopes is called a baseline, and the wavelengths that they observe depends on the distance between them, and the orientation, the kind of spinny roundness of the waves depends on the orientation of the baseline as well. So these two baselines here would be perpendicular, so they would give you waves of the same length, but spun around 90 degrees. And so what we do with interferometry is we measure those Fourier components, those the amplitudes of those wavelengths, and then we use that information to rebuild the image of the sky, just like we saw in that video. But the difference is that you don't have access to the infinite wavelengths that you need to do the reconstruction perfectly. So if you just do a snapshot observation with your telescope, you observe the wavelengths corresponding to these points in the plane. So these are to do with the length of the waves, the wavelength of the waves and their orientation, just represented in a plot. As the Earth rotates, if you let the telescope keep observing while the Earth rotates, you can see that these tracks are going to sort of follow circular paths, because they're going to be pretty much the same length, but the orientation is going to change. And so we call this filling up the UV plane as the Earth rotates, and that means that you get a better and better reconstruction of the image, the more and more of those wavelengths you can measure. So this is a pretty difficult mathematical concept. Don't worry too much if you didn't quite grasp all of that, but hopefully you got the idea that you're reconstructing the image out of these Fourier components. And so the idea that the Earth rotates and it helps you to do that is called Earth rotation aperture synthesis. And so Ryle developed the principles of the aperture synthesis technique. So this is Ryle of the Nobel Prize. There's an asterisk here, which is kind of funny. I'll get to that in a minute. Which were implemented by another member of the group. So he was kind of the theory guy, not the computing guy. His ideas were implemented computationally by John Blyth in 1957. And Blyth's papers credit a Mrs. J. Sandos, who performed most of the analysis. So the reason why this is so computationally intensive is that you need a lot of processing power to take those Fourier components and stitch them back into the picture. And at the time, those techniques to do that were just under development. So it was really at early days of this kind of analysis. So what they did with these interferometers, once they had developed this technique, was to go and make surveys of the radio sources across the sky. And radio sources are not stars. Radio sources, the bright things that you see in the radio, are mostly active galactic nuclei. So these are the supermassive black holes at the centers of galaxies, gobbling stuff up, spitting stuff out. And so what you're seeing in the radio sky is all the extragalactic stuff, right? You don't see that much of the stuff in the galaxy. And so these source surveys provided quite compelling evidence against the steady state hypothesis, which was one of the sort of well thought of models for the universe at the time. The steady state hypothesis said that the universe was expanding. Yes, they knew that at that time, but everything was otherwise staying the same. Right. And so you can imagine that if you look very far, if that is the case, and you look very far out into the distance, you can calculate what brightness of sources you should see as you look out into the distance. And they saw something that was not that. And so that told them that things were evolving and changing. And that was seen at the time as a piece of evidence for the Big Bang model, where things started, the universe evolved over time, things changed. And so when you look out in time, you back far enough out in space, you're looking back far enough out in time, radio sources haven't developed yet, essentially. So you can see that that would produce a difference in the number of sources that you see across the sky. Contributions to this work also came from a bunch of PhD students, many of them female in the group. The asterisks, I found out while I was doing a bit of reading for this talk that actually Ryle had a male PhD student called Hogbom who did some of the stuff ahead of him, and he just completely ignored him. So at least he was an equal opportunity thief of work. Yeah, and again, just one final complication. What you see in your Fourier transform is a flat Cartesian coordinate system. So it's a flat patch, X, Y coordinates. And if you want to map the sky accurately, you have to know how to convert to spherical sky coordinates. And then you have to know how to plot those on some kind of contour map. So this is the North Pole survey from one of those early source survey works. So you can see you're looking up in the sky, you've got like a spherical cap, you need to know how to do that transformation correctly, and you have to be able to tell your computer to do these plots. So Liz Waldron was one of the people who pioneered these techniques to do the plotting properly and plot a contour map. And I know Liz very well. She's still at Cambridge, she's still an active researcher. And so I'm not a computer graphics person, but I have read that this was pretty much the foundations of modern computer graphics. And she was one of the pioneers of that work. And just as a counterpoint, flexible working around childcare was possible at the Cavendish. So Liz had children and she was able to work part-time around her children. And, you know, in a way that we would think is normal now. So not all bad at the Cavendish. All right, so that's pretty much the end of my talk. But I got to the end and I thought, who have I missed? I've missed all the Americans. So if you've ever done any reading on women in astronomy, you'll know that there are a bunch of really important contributions which were made by American women in particular at the Harvard College Observatory. People like Annie Cannon developing the stellar classification system, I don't want to use the acronym because it's not very nice, the OBE, that one. People like Cecilia Payne-Gaposchkin, who completely revolutionized our understanding of stellar composition with her work. People like Henrietta Leavitt, who discovered a really important relationship between the period and luminosity of a certain type of variable star. People like Vera Rubin, who provided firm evidence for dark matter and galaxies. A bunch of people I've missed out. So apologies, I did say it was going to be incomplete and personal. But there is a fantastic book about these ladies if you're interested in finding out a bit more about them. And finally, you cannot do a talk on women in astronomy in New Zealand without mentioning Beatrice Hill-Tinsley, so I saved her for last. She was born in England but moved to New Zealand after World War II and spent much of her early life in New Zealand. She did her undergraduate and master's at Canterbury University. And then she married a physicist who was also at Canterbury and had done his PhD. He got a job in Texas, and so they moved there. She didn't like the department and ended up commuting 400 miles every week to complete her PhD in astrophysics at the University of Texas at Austin. She was the only woman in her program. She was ferociously determined to do her PhD in astrophysics and somehow made it work. I cannot imagine commuting that amount every week to do that. So she really pioneered work on the evolution of galaxies, how galaxies change with time, kind of similar to what I mentioned before about the radio sources. And her findings contradicted Alan Sandage's cosmological theories, and he was one of the really big names in cosmology at the time. And he used the brightnesses of elliptical galaxies to show that the universe was contracting and we were going to have a big crunch, which is quite a important thing to know. But what she realized was that he was assuming that the stars and the galaxies were the same over all cosmic time. And like I said before, things are not the same over cosmic time. So she really pioneered our understanding of how our observations of galaxies change depending on how far away they are and therefore how far back in time they are. she constantly struggled to find a job due to anti-nepotism policies. So because her husband was employed at the first university in Texas, I forget the name, they wouldn't employ her because it would look like nepotism. And so read into that what you will, whether it's nepotism or discrimination, but she really struggled to find a job despite these incredible contributions and pioneering work. And eventually she accepted a job at Yale, which was quite some distance away, too far to commute. And to do so, she had to divorce her husband and give up custody of her children, which is incredibly sad. Again, a sad ending. It must have been, I just can't imagine having to make that decision between your career or your children. And I feel so lucky that we don't have to do that these days. Or at least I have not had to do that. So again, a bit of a sad ending. Died relatively young of melanoma, but is very much remembered. And I think in the past few years, there's been a movement to bring her more to the forefront of our minds in New Zealand, because she's someone that we should know about and we should celebrate. And so again, a nice book to read. And I know someone who has a copy in their bag right now. Right, so I'm going to leave it there. I just wanted to end with a little montage of fairly randomly selected women in astronomy that I know or know of today. You might recognize some faces in there. And thank you very much for your attention, and I'd be happy to take any questions. Sydney.